So my name is Dylan McKenzie. Hello. So I have the great pleasure and perhaps the challenge of introducing our next speaker, Jeff Mishtawy, excuse me. Jeff is part of an ongoing tradition here at Practice, something that we affectionately refer to as our left field speaker. So we're here at Practice, game design in detail, right? So we're here for depth and for expert game design, but there's a conflict because another part of our goal is to explore games in their many forms, in their breadth, something you can already see from all of the range of talks that we've had this morning and yesterday. So the challenge of our next speaker, what he's generously been willing to do is to take on this challenge of sharing the depth of his process with a group that's unfamiliar with his tools, with his players and his game, and with his challenges. And I think that's a question of literacy, right? How do we get to depth without understanding exactly what it is that it takes to get there? For example, people tell me that Dota is a really deep game, and I've tried, but it just looks like a lot of nonsense to me. But I'm sure that it is deep. I believe you all. I just can't watch that happen and really enjoy it. And the game that Jeff works on is car racing, and something that to you may read like Dota does to me. But I think that car racing is maybe not as different as we all think. First of all, many of us know how to drive a car, so we know the buttons, right? That's a start. Many of us have taken some liberties with the speed limit, so we know what it feels to go fast and the concentration that's required to maintain that safely. And maybe some of us even felt what it feels like to lose control of the car a little bit on snow or ice and then regain it. So you have that sense of the limit of traction and that search for adhesion that's so central to the experience of car racing. So even if you're, or if you haven't even driven a car, you've maybe been in a foot race or you've kind of jostled on the sidewalk, and so you know what it feels like that kind of tug in the back of your brain that wants to be there just a little bit before the person that's next to you. So what I'm saying is, even if we aren't all race car drivers, I think that we all have the fundamental literacy that we can use to enjoy learning about Jeff's practice, his game design process. And I'm personally very excited about this talk because as a game designer and a race car driver myself, I found so many analogs between these two things that I love that I've wanted to share with you all for a long time now. I think that the way that sports amplify and kind of funnel the sportsmanship and the decision making, or the excellence, the math and the deep knowledge that's required to create a strategy that will take a car from the start of a race to the end and not have it crash or stop moving. And talk about a series of meaningful choices. The experience of being a race car driver is like meaningful choices in a centrifuge. It's just happening so fast. And I think that Jeff is a master of this knowledge. He's an accomplished behind the wheel as a race car driver. He's won sports car races across America. As a team leader and a chief strategist, he owns more than 60 top 10 results in various sports car classes since 2007. As the director of motorsports at APR, he managed a 6-car team, which, believe me, one car functioning is just a tremendous challenge. So 6 cars is incredible. Not only that, he has 9 race wins and a second place finish by 1.4 seconds at a 24-hour race in Daytona that I had the pleasure of seeing in person. So today he's the senior technical manager of the IMSA Continental Tire Sportscar Challenge, the same series that he had that second place finish in at Daytona. He plays a key role in writing the rules and devising the enforcement methods and refining the balance of performance process at what I believe is one of the most interesting and exciting car racing series in the whole world. And he gets to make games with real race cars, which is pretty cool. So it is my pleasure to introduce you to Jeff.
How's it going, everybody? Jeff Mishtawy. For those that don't like car racing, this is probably going to be the most boring talk that you're going to have all weekend. If you walk into it with an open mind, maybe it'll be mediocre. So hopefully we can draw some similarities between what I do, what we do as a series, and the talks that I've seen since I arrived here earlier. So, I'm, again, Jeff Mishtawy. I live in Daytona Beach, Florida, home of NASCAR. That's who I work for ultimately. You know, I started racing when I was about 12 years old. Dylan kind of covered some of my history, but I was a little kid. I played with radio control cars, and I got to be pretty good at it. One of the top 10 in the country in off-road racing. And then as I got older, I started to volunteer as a crew member. Eventually, I became a crew chief for a team. Then about the same time, I was also interested in driving. Every little kid, right? Every little kid wants to be a race car driver. They see the Indy 500 or the Daytona 500, and they want to get in a race car, and they think, yeah, you just show up and you drive the car really fast and you have a lot of fun. And the girls are everywhere. It's not really the case. Although my wife Becky is fantastic and she's really super supportive. Thank you, Becky. But eventually, I realized I had as much fun in the driver's seat as I did behind the scenes. So when it came time to make the decision of where do I want to make my living, it was pretty easy. It was behind the scenes as a team leader and a crew chief. Over the years, I've built and developed a number of car racing teams, and it's all built on the same fundamental philosophies of the majority of which I'll go to here in a moment. After several years of team management, I was approached by a company called IMSA, that's the International Motorsports Association, to come on board, and in a way it was kind of sold to me as find the bad guys, asterisk. The asterisk means, by the way, you kind of also have to make sure everybody has a shot at winning. You don't just find all the guys that are cheating. So when you look at this picture, you see a whole bunch of different cars, and everybody's got to have a shot. Everybody has to have a shot at winning. So with IMSA was it's a long-standing company. It was founded in 1969 by two guys, a guy named John Bishop and a guy named Bill France Sr. I don't know if anybody's ever heard of Bill France Sr. He's the guy that started NASCAR. Small little company there. Their first race attracted 348 spectators at Watkins Glen. It's in upstate New York. And since then, the company had been bought and sold a number of times. Over the years, it eventually became the American Le Mans Series. Then the next step for the France family was Jim France. That's Big Bill's son, wanted to go sports car racing again. So he started another series called the Grand American Road Racing Series in about 2000. At the time, Grand Am Series and the American Le Mans Series were direct competitors. I mean, they would block each other out of venues. They would make sure that their cars never got to the same tracks. So nobody could compare lap times, and it was kind of a brutal rivalry between the two companies. But in 2013, the two companies got together and merged. So Grand Am and IMSA became one, and because of that, several different entities were combined. So this is our home base in Daytona. And as IMSA raced over the years, these were some of the iconic cars from the 70s and the 80s and the 90s that some of you, if you've ever paid attention to any kind of racing, some of you may have seen before. But what IMSA does, other than the prototype cars that everybody knows, is the Continental Tire Sportscar Challenge. And in the Continental Tire Sportscar Challenge, there are two types of cars. So literally on the track at the same time are two different classes. They're not racing against each other. They're racing against the other competitors in their own class. The faster of the two classes is called Grand Sport. Those are the Porsche 911s, the BMW M3s, the bigger, proper sports cars. Then the Street Tuner, which are the Honda Civics, the Audi S3s, the Mazda MX-5s, the smaller, lighter, lower-powered cars. So they all share the track at once, and they occasionally clash on track. We don't like seeing that too often, but it does happen. I mean, occasionally you got these GS guys when they're super fast cars coming by the little Mazdas on the straights and on the banks of Daytona. The GS guys are doing like 200 miles an hour, and the MX-5s are doing like 120, and it gets a little scary sometimes. We don't like to see that. So when I came on board, I was a crew chief. As a crew chief, and especially as a successful one, you don't make a lot of friends in the paddock because everybody wants to beat you, and if you're beating them, then obviously you're cheating, or obviously you're doing something different than they are. And it turns into a bunch of bitter rivalries. So when I came on board, the first thing I did was call all the crew chiefs and all the team owners and make sure that they knew that I was no longer an arch enemy, but I was there to work with them as an official. And I'll never forget one of the first conversations I had was with somebody I'll call Michael. That's not his real name, but somebody I'll call Michael. Michael was adamant with me. He was just so upset about the current, what we call balance of performance in the GS class. His driver, an absolute top line driver, was behind a driver in another car, different kind of car. Also another absolute top line driver. Michael was just screaming at me on the phone that my guy, I couldn't get around him unless he made a mistake or we forced our way through. And I let him go and go and go, and I made him repeat it again. I couldn't get around him unless he made a mistake. I said, Michael, are you listening to what you're saying? It sounds like the cars are pretty equal, right? That sounds balanced. Well, it hadn't really occurred to him. That's what we aim for. So he thank you for doing my job for me, Michael. That is exactly what we're aiming for. And since then, Michael and I have had a rocky relationship. But but it's it's what we do. All right. So balance of performance. When I came on board, there was no target for this. All right. We had to define a way, or some way of measuring performance. In the past, it was this old school approach where everybody would look at lap times. It used to drive me crazy when I was a racer, because the series would look at all these lap times for all these different cars. Right? Each car has its own rule book, and the series changes the rule book for each car to make sure that they can all race against each other. So we needed to find a better way of collecting all the data, and how do we organize it? What we have here. This is from the 2012 London Olympics, and of course Usain Bolt's going to win everything that he touches. But the difference between Usain here and the fourth place guy here is roughly the difference that we try to keep all the cars within over an average of 20% of the laps of the race. Right? So I'm going to give you a quick sample of what that gap is. Well, that didn't work. Let's try this one more time. That long. 0.6 seconds on a 1 minute 40 lap. Or 0.7. But that window, that little beep, is what we have to take into all this fury, all the engines, the tires, the downforce, the drivers, the mistakes, the curbs, the gravel on the road. That's the goal that we try to keep everybody, the window we try to keep everybody within. It's a tough one. But before there was never a goal. It was only, well, the cars look fast. There's like, it might work. So now we're a little bit more advanced with it. So, balancing performance, what is it we really do consider? There are theoretical data points and things we can measure on the cars that may not really exist in the race world, and then there are measured factors that we can pull out of the race data itself. So we'll go into a little bit of both the fields and how we merge them together, and then how we arrive at a performance balance. Because, well, let's face it, racing at its core is an extremely interactive, extraordinarily expensive, and freaking dangerous game. I mean, this is one where people can get seriously hurt in this game. And people spend millions, literally millions and millions of dollars a year out of their own pocket for usually there's not some big sponsor, it's the driver that's funding the deal, to come play this game. And it gets a little addictive, and because of that, people get kind of pissed off about it occasionally. So, some of the isolated data points that we look at, you go to this place called Shear, and this is in Concord, North Carolina. And Shear is a rolling road wind tunnel, one of the only ones in the world. So notice these little black marks here? Those are from the tires. And these struts are connected to the wheel hubs. And you notice this little line back here. This whole device, right, this road runs at 150 miles an hour. The air blows at the corresponding speed. Then the whole table itself turns into the wind, so we can measure the offset of the car. We can measure downforce even when the car's not going straight forward. We did a couple studies and found that most race cars are rarely going straight. Even when they're cornering, they're sliding a little bit. So we had to learn to measure downforce and drag and all these characteristics as the cars are in yaw also. So when a car is new to the series, we do all these measurements at Concord, and we normally spend an entire day with each car, and it's like, I think it's like $2,500 an hour to run this thing. And then one of the other this is an important one. Some of you guys and girls may have seen a chassis dyno or an engine dyno before, but at the NASCAR R&D Center, also in Concord, North Carolina, we have what's called an inertia dyno. And an inertia dyno is there's 6,000 pounds of steel plate in here, and then an engine here, and then this is it's called a transmission, but it's not like a transmission in a road car. But what this does is it applies a load to the engine unless you run the engine outside of the car. So you can measure all kinds of characteristics: power, torque, RPM. You can make changes to the engine and make and record the differences. Before a car and an engine goes to race in our series, we have to do all these measurements to even know what in the world we're looking at or what to expect. And when we're done with the dyno runs, this is what gets spit out. Again, some of you may have seen a dyno sheet before, but probably not one like this. This is from a manufacturer, name withheld, that we ran about 10 different restrictor sizes, and the corresponding colors up here. This is the horsepower, this is torque, right? And so you see all the different brakes and power when it comes to, and torque when it comes to different restrictor sizes. So we can, for those that don't know, a restrictor, it simply just blocks the air coming into the motor. So the less air that goes in, the less power it makes. So we can control how much power it makes by adjusting the size of the restrictor. So if somebody's showing too much straightaway speed in the race, we can pull the restrictor back a little bit, and it'll slow the car down just a touch. But probably shouldn't mention this, but I left this slide up here because this, when we asked them how much power do they make, they reported this when it was actually this second line up here. This is why we verify. Trust but verify. Sneaky racers. All right. So now we have some of the theoretical data, which is, we know downforce, we know drag, we know horsepower, we know torque, we know the weight of the car. We have a number of different weights of the car. We can kind of create whatever we want. So back at the office, one of our engineers, his name's Matt Kurdock, and Matt deserves he's an amazing guy, that he came up with this concept, and then Scott Raymond and myself went one step further with it. It's called tractive force analysis. And what tractive force analysis does, it combines all the items that we measured and creates a fully predictive graph of engine acceleration or vehicle acceleration in each gear. So some of the cars have 6, 7 gears. And what we're going to look at on the next slide here is tractive force. It means accelerative force at any given speed, right, from 50 to 300 kilometers per hour. And over here we have acceleration in meters per second squared. So this is the whole field right now in one of our classes, and you see all these little steps. That's every time the car shifts, the rate of acceleration decreases as speed increases. So everybody's in this real tight little window for the most part. So anything over 60 miles an hour, everybody's almost identical. And this is verifying what we see on the track. When we see good racing on the track, the cars are almost identical here. When we see somebody running away with it and they put 20 seconds on the rest of the field, then that car is usually out here somewhere, and that means we have to slow it down a little bit. So that's not what we're aiming for. So, all right, now, yay, we've gone through all this stuff. We have all the theoreticals. We have an initial balance for the car. It's got to run this restrictor. It's got to run this weight. It's got to run this RPM. We run the race. Now we have to go home. We have to digest all the data. Now this is where it gets really interesting, because we have all the theoreticals in place. Now the rubber has met the road, and sometimes the grass, and sometimes the asphalt, and occasionally the air. Everything but the ground sometimes. But we go home, and then we look at, it used to be just lap times, but now we've taken it like 10 steps further. And I got to say, a lot of this was driven by, when I was a kid, I was playing Need for Speed. Probably shouldn't have done that as much. So with lap times, sector times, trap speeds, I'll go into the definitions of these other items: eclectic, rolling, and then we also have data recorders in the cars. We pull all the data out of those and look at how the race was run from the pit box. So I'm a strategist. I understand that can affect how the race turns out. If you notice back in that last slide, race results aren't in there anywhere. And we don't, just because the car won doesn't mean it was the fastest. That means it was best run. So usually race results have absolutely nothing to do with balancing performance. That's a product. That's a function of team execution, and we reward the teams for that. So this is one of the tracks that we go to every year. It's called Circuit of the Americas. Has anybody been to Austin or Circuit of the Americas? Couple. Okay. All right. Everybody loves Austin. I mean, hey, we stay an extra week every time we go. It's a great town. All right. So at Circuit of the Americas, there's a basic 3.4 mile layout, and as we moved into 2013, we decided to collect more data from the track. So we started to make all these little cuts in each of the tracks, right? And what these are, they're little antennas buried under the track. And each car carries a little transponder, emits a digital signature. So every time the car crosses one of these stripes, it creates a data point. Right? So then we can look at a number of different real-world measurements. So we can, these two here are speed traps. So as the cars go down the straightaway, we can, with a fixed distance, we can measure speed, right? Distance over time, and 2 different places. And then we can look at cornering characteristics. For those that don't know, this corner here goes like 300 feet up in the air and then dives back down. It's like climbed a skyscraper. It's kind of crazy. And then these are all high-speed S's, more cornering, and long straight acceleration. So it lets us cut the track up into different areas so we can measure vehicle performance. So from all the sector times, we can generate massive amounts of data. So we build a little script during the race, so we can actually look at some of the stuff as the race is running. Here's just an example. This is a Coda again. Fastest race lap. This is average. Like each car, our races are 2.5 hours long in general, so they turn a lot of laps. So fastest race lap, average of the top 10 laps for that car, average of the top 20, average of the top 30 laps. All the colors over here. Each manufacturer is color-coded. So we can take a glance, and all the blue ones are Chevrolet. So you can take a look right across and look at where Chevrolet was, just at a glance. Then we also measure what's called rolling lap. So going back to the map, like rolling lap would be, let's say instead of this is the real start-finish line. But let's say we make the start-finish line here. How does that affect lap time? Right, it affects it pretty dramatically. Sometimes on a fast lap, the guy may make a mistake, but then on the next lap doesn't make a mistake in the same place. So lap time is really vastly different than a rolling lap time. The next one is eclectic lap time. Now what eclectic is over the whole 2.5 hours, what if we took each individual best sector for that car and added them all up together to see how fast could it possibly go if they did everything perfectly? Okay. Oftentimes it's really fast. It's like usually a second or two faster than they can really go. Because like in order to make this sector here really fast, you might have to blow the exit, and you can't actually do enter this section with the speed that you would need to. So sometimes it's a little bit blurry. It's a good data point, but sometimes it's a little unrealistic also. Then other ways we look at averages, right? The fast laps numbers 2 to 11 and 12 to 21. So that's excluding the fast laps. What that does, it shows how the car slowed down. Like as tires started to wear, how does the car degrade? How does it slow down and fall away? This is where the drivers get pissed off, is when the car starts to slow down and they're doing everything they can. The car just won't go any faster, and the other guy on new tires is driving away, and then they come yell at me because this is just crazy unfair. So we keep a close eye on how the cars fall away. Then these two boxes over here are top speed. And these are 2 different measures of it. Everybody would say, well, the fastest car on the straightaway is going to win the race every time. And in a second, I'll show you why that's not the case. But also with fastest on the top, the fastest individual result for a speed trap is the effect of the draft. Let's say they got bumped by somebody from behind and they had an artificially high speed trap number, or they had a big car in front of them and they got a great draft and again, returned a great individual result. That's why we also look at the top 20% of passings through the speed trap for each car. As you see here, the Nissan led speed trap individual and an average. This Nissan was a rocket in a straight line. But fastest lap, the Porsche got it. And the Porsche was actually the 4th fastest and the 6th fastest in the speed trap. It's not just about the speed trap. For each of the sectors that we showed you, like how the track is all split up, We also do full analysis of each one. So we assign a value to straightaway sectors, curvy sectors, braking sectors, and then we look at fastest, average of the top 10, average of the top 20, and average of the top 20%. And again, you see the Nissan, sector number 1 is a straight. The Nissan just kind of kills it here. The Camaro, which is lost in the sauce down here on the straightaways, is wicked fast on average on the in the corner bits. So we also carry data loggers on the cars. I'll show you a little bit of that. So we own these data loggers. They're called a DL1. I'll show you more detail in a moment. But without getting too lost in this is a track called VIR. It's in Virginia, and the Camaro guys looked at the speed trap numbers that we saw, and they say, "Hey guys, we can't compete. I know we just won every race in the world, but we can't compete because our car is 6 miles an hour down on the straightaway, but you guys are only like 0.008 of a second off in lap time. I mean, this seems like a fair trade." So we did a little bit of a study, and what we're looking at here are 2 different cars. The blue line is the Porsche, and the red line is the Camaro, and this is actually taken from the race. Okay, so this is a speed trace, and what this is called time slip. All right, so this blue line, we assumed the Porsche is the 0 line. So anytime the red line's below it, it's losing time, and if it's above it, it's gaining time. Actually, sorry, reverse that. So when they accelerate out of the corner, they were level at about here, but sorry about the zoom. So the Camaro pulls a big lead right out of the box up to about 100 miles an hour, and then the Camaro and the Porsche starts to pull the Camaro back in. At the very end, the Porsche is just slightly faster than the Camaro, and that's what the blue line shows up here. So this is, although the Camaro is way down on the straight speed, the Porsche has about the same elapsed time on the entire length of the straightaway as the Camaro. So we have to balance that. Now, if the straight's shorter, the Camaro is going to have an advantage. If the straight's longer, the Porsche is going to have the advantage. And we have to find a way to balance it so everybody fits into that one little beep window. And looking a little bit further on the DL1, this is back at COTA. And that we run, the teams hate these, by the way, because every weekend we show up and they don't know if they're going to run one of these things or not. So we'll send our crew, our officials out, and we'll say, "Hey, you guys got to run this box this weekend." It's a little box. It's dual accelerometers and a GPS that goes on the roof. And the teams always think we put it in their cars because we think they're cheating. It's not the case at all. We put it in their cars because we want to see how a Camaro compares to a Nissan. So we always run these little graphs afterward. And this is the speed trace for the track. And all the cars here are lap times are within a couple tenths of a second. And as you see, they're all made up radically different. So some cars are really fast on the straights. There are big differences in the minimum speeds in the corners. But it's that's what we aim for in balance, is that it's give and take. This isn't everybody racing the same car. Everybody's racing completely different cars, but they have to be within the box. Okay. Now each car on their own, each team uses something called this a MOTEC or data logger, and part of the entrant agreement is that any data that's produced by the car is our intellectual property. So when they sign up to get their credentials and they pay their $4,000 to go racing on a weekend, they provide they're required to provide us all the IP that the car generates. And on this particular graph, we look at a number of higher level variables. So speed trace, like we saw in the other box. This is also engine RPM. So we can make sure that they're actually using all the RPM, that they're not short shifting or they're not running artificially slow, so it looks like they're slower than they really are. So we help them out on the rules. It's called sandbagging, and people make a living at it. We can look at how the driver applied the throttle pedal, the differences. The temperature of the water. We can look at ignition advance. We can look at what's called lambda, which is how rich or lean the fuel mixture is. And then we also look at things like this vehicle speed. So up here is one lap, and down here, this is the entire race. So when you look at all these little peaks with the vehicle speed, this is the start of the race, right? When they're behind the pace car, the race starts, and they're racing. They go to caution. They go racing again, then caution again, racing, caution again, then all this long stint of racing. This is important because it's rare we have a green flag that's this long. And we also look at what's called map position. So those guys, like in the car, they can change the software. they can change how much power the engine makes. So we can monitor what they're doing. So we can look here and we see that they started the race behind the pace car. They were in map 1. They switched to map 2, went back to map 1 under caution, map 2 racing, map 1 under caution. So it's obvious map 1 is going to be the fuel saving mode, and map 2 is the performance one. We monitor how much fuel they use on each lap. Again, when they go to yellow, how much fuel consumption is down, and then engine temperature over the entire race. And then predicted lap time. So the data loggers on the cars are actually quite advanced. They tell the driver what their lap time is going to be before they actually finish, right? Which, I mean, it's great, but for us, it sucks. Because if some of the teams that are really good about hiding performance, looking at all the data, this is assuming that everybody's trying as hard as they can. Well, I mean, what if they don't? What if we have this whole trend of, let's say a BMW that didn't perform as well as other cars for 3 or 4 races in a row? We'd take some weight off the car, or we would give them more power. Well, now they've kind of fooled us, so we have to look super deep and find out if they actually used everything that they had. And it's that predictive lap time. I want to write a rule to make that thing go away. Okay, so we've now done all the theory, we've applied it all, we've run the race. And then we have to take into account now the imperfect real world, and occasionally cars end up on their lid. But other things can happen in a race that really screw up the data, and the weather, collisions, the timing of cautions. I mentioned in the VIR Motec data that there was a very long caution, and because of that, all the teams had to pull back a little bit on the speed of the car, so they were trying to make it to the end on fuel. They're about to run out, and we only let the cars run 55 minutes on fuel. That's our target. So in a 2.5-hour race, they have to stop and refill. So they stopped early to refill, and they stopped with an hour and a half to go, and they only have 55 or 60 minutes worth of fuel in the car. Ooh, they had to stretch to get there somehow, or come in and fill it up later. Then there's the human element, the driver, the driver that just having a bad day, the crew member that couldn't get the wheel nut on in time, or the guy that screwed up the adjustment on the setup pad and the car's just running slow because of that. And then the other things, the vehicle configuration. So like a Porsche versus a Camaro. A Camaro is a big, chunky car, huge V8 engine. I mean, massive V8 engine. Guys, I could barely fit it on this stage sometimes. And the Porsche has got this little tiny 6-cylinder. It's hung way, it's literally behind the rear wheels, the engine is. It's way out back. So it's slippery aerodynamically, low frontal area. It accelerates really well. Has high top speed, but the Camaro has brute force coming off the corners with all that big motor. So in a second, I brought some video. Hopefully I don't bore you to death. That shows some of those differences. All right, so here is the rain race. This is going to be one lap of a race that kind of illustrates how much rain can impact what we do. I can hear you. All right, well, we're going to go without audio. But it's not really terribly important. What you can see is it was pouring this whole race. 2.5 hours, this is 10 minutes to go. Or maybe we'll get a time here in a second. But you can barely see the cars back here, even with headlights on. So we have just huge amounts of water on the track. We have cars squirming all everywhere, and nobody can see anything. And some of the in-car, it's brutal. What we're in now is the 15 car, and the 15 car had one of the best averages during the race. This is a Mustang Shelby GT350 factory Ford race car. There's all this water standing everywhere. BMW, Camaro. Now in the rain, anytime it rains, we throw away the data because there's no grip. The power's turned down on all the cars because you simply can't use 500 horsepower right now because all you're going to do is spin the tires. And in fact, we're going to see in a moment, we're going to see a really good illustration of what happens when you try to use 500 horsepower in a car in the rain. So pay attention to this Camaro here. Now these guys have the same power to weight ratio. So it shouldn't be any big massive difference. But what happened was he spun the tires because he got on the accelerator too fast coming out of that last corner, and he's a sitting duck. So now, because of that, because he didn't have the grip, the Mustang's able to go right by. But nobody can see what they're doing. So on the radio right now is his spotter telling him when to turn. Right? So he almost missed it. And then it's going to continue a little bit. The Camaro kind of pulls him back. But again, see how equal everybody is. It's even in the rain, everybody's really freaking close. All right. So that's an example of how the rain can screw up the data. Because now, I should mention after the race, the Camaro driver that got past was absolutely like red-faced, screaming at me about how unfair the world is. And then I pulled up, I went and grabbed the data, looked at it, and I said, well, here's why. You knucklehead, you put it on the gas too fast and look at all the wheel spin you had. Well, that'll do it. Okay, so on this one, occasionally we have these other issues. So the Nissan here qualified second in the race, by the way. They've never won. They always do this stuff. Right? And if Brad was here, I'd say the same thing. So he runs off, spins. The Mustang was trying to avoid it, and he takes that big shot right there, right? And right in the wheel. Now, here's the onboard from the Mustang. So he hits the Porsche and spins around, and then, bam, takes a big hit. Okay, that was enough. Usually that's enough to end somebody's day. Now, this is the championship winner, by the way. He does what he champion winner does, and he avoids everything. But this was what happened to the Nissan. Well, the reason why I showed you that clip, guess what car was the fastest on average? That was 15 minutes into the race. Guess what car was fastest on average in that race? That Mustang that got hit. Yeah, he took that big hit on the front suspension. We have no idea what it did to the alignment of the car, or if the car was all bent and tweaked. That was the fastest average car in the race. So we got home, we saw the data. What in the freaking world is this about? So did they like knock it into adjustment? We don't know. So we have to we have to look at that with a big grain of salt. And sometimes those off-track excursions, we have to. I always say it's keeping an eye on the racetrack. There's the data, but then there's the practical application. We have to look at actually what happened during the race. Because had we not actually seen that, we just saw that the car had led the data, we may have adjusted it. But because of the off-track and the hit on the car, you don't really know what happened. Especially because with the crash, he finished low enough that we didn't impound the car afterwards to do all their measurements. We'd have never guessed in a million years that a car that had been crashed would be the fastest car on average. Everything, I tell you, you get surprised a lot. Okay, so what the goal ultimately is equitable racing for everybody. Because be it players of video games or the players of our highly interactive, very dangerous, very expensive game, they all want a shot. Right? They all have to feel like they can do it. If it's a hopeless exercise, they're not going to show up, and they're going to vote with their dollars. I won't have a job. So we have to keep them engaged, and that's, I think, the biggest similarity we have. There are players of every game, and they have to feel engaged in it. They have to feel like they have a chance. I can't tell how many games I haven't played because I played that 10 minutes. I'm like, there's no freaking way. But oftentimes, what it takes to keep everybody engaged isn't what the data says. Sometimes the data says very clearly, this is the decision we need to make. Sometimes we got to throw a team a bone and help them out a little bit to keep them in the game. But occasionally we get it right. Now, guys and girls, this is 4.5 minutes, and for some folks it's going to be painful. It's going to be super boring, and guys, I'm sorry, but I wanted to show this one. I cut it down from 12 minutes.
I think we can get the sound out of the speakers. I think it's going to the projector right now. So if we just switch it, it should. Because if we're going to watch for 4.5, the sound's nice.
Yeah, you're right.
Even with them, yeah.
All right, so let's try that. Oh, no. Guys, I failed you. Well, no, it's... Okay. Well, we're just going to fast forward a little bit through it, so apologies. Right, so what's happening, and the reason why I did this shows you both classes that are racing. So this is a street tuner class. So these 5 cars here are leading street tuner, right? Leader, second, so on and so forth. These cars over here are leading Grand Sport. So the Camaro, the Mustang, and this is a Nissan. And I picked this one because it really clearly shows what good performance balance is. These are literally 3 identical cars. Right, I mean, they are the same MX-5. They're run by 2 different teams. It's the same car. Over here, we've got 1, 2, 3 cars completely different. A 7-liter V8, a 4-liter V8, and a 3.7-liter 6-cylinder engine, all racing, all climbing all over each other. So with effective performance balance, regardless of if they have the same car or entirely different cars, we can have a good race. Then this... I was in the 2015 season, I thought the best example of it. Because when we get in 3 minutes, when we get to the end of the race, these 3 cars are going to be more tight in finishing position than the 3 identical cars. So the Camaro is big and brute force, and when you see the end cars, you'll see it leave the Mustang just when they get to power. The Nissan has great speed at the end of the straightaway, but can't quite get it. The MX-5 just like ping-ponging off each other. And the Honda back there is, if they would stop racing against each other, they'd drop the Honda in a heartbeat. And all right, so coming into the final lap here. All right, all 3 of the cars right on top of each other. I talked to all the drivers afterward. They all had a hell of a good time, and nobody can make a move. I couldn't I couldn't get around them, but nobody's getting left either. Everybody stays right together. So the Chevy guys, the Chevy guys are obviously really happy here at this point in the race anyway. And but at the end of it, regardless of the finishing position, they all were. So last lap, last couple of corners, Camaro is just shot. It's really heavy. It's hard on his tires. And the Nissan, I talked to BJ afterward. He said, I was just sitting back thinking that they're going to take each other out. So I'm like, I could have got in there, not going to mess around with it. So when I watch what happens, the initial acceleration, the Camaro just pulls straight away and pulls a little bit of a gap, and that's the end of it. So take a look at these 3 cars when they cross the stripe. Yay, beers, cheers, all right. All right. And then as we come down the hill, if you guys haven't been to Laguna, you're coming down 5 stories, and in those 3 corners, it dives down. The camera really flattens it out. So these 2 cars, last couple turns, and then so like that miracle move. But that's going to put, see how they had pulled a big gap on the guy in 3rd. And remember that the finishing gaps for the GS cars is slightly bigger for the identical cars in ST. So I thought I walked away from that weekend thinking, you know what, we did all right. But one thing's for certain, we've had to adapt racing and what our expectations are. And we're going to have to continue to. Racing, as far as production cars go, had sort of plateaued in some ways, and now we have to look at what's going on in the real world. The cars are gearbox technology is like leaps and bounds. I mean, it's really, really growing. So we have to find ways to adapt it into racing. What happens with hybrid? What happens if somebody wants to race a Tesla? Are we going to just prevent it? What if every car becomes fully electric? Well, at some point we have to learn to adapt these things into what we're doing. I mean, I keep going back to Tesla because it's a great example. Like one of the features on the car, when you're at highway speeds, the door handles retract into the doors to reduce aero drag. Like, that's pretty slick. But, are we going to prevent that kind of stuff, or do we let that into a controlled environment? How does that affect our performance balance? What do we know about fuels that are coming, or what's the X factor? What's coming next in the automotive world that we don't know? I mean, yeah, I'm all over Jalopnik, but I can't predict 30 years into the future of the automotive world. So we don't know what we don't know, and it's terrifying a little bit. But the first car race ever, does anybody know what that was, by the way? The very first car race ever in the history of mankind? I don't know either. Right. But I was just honestly asking. Yeah. We can probably figure it out, though, right? It was probably two guys that had cars. And well, obviously, and they were probably neighbors, and one of them said, mine's faster, right? And then they raced. It wasn't a professional deal. It wasn't. They didn't have pit crews, and they didn't race the Indy 500 as the first race ever. Regardless of whatever changes in the automotive landscape, be it everybody with full hybrids, alternative fuels, fully electric, hydrogen-powered cars, everybody's at some point going to wonder who's faster. And we have to adapt our world, be it in data analysis or the acceptance of new technologies in motorsport, to create an environment that everybody has a fair shot at winning. And that's really what we aim to do. So, open the floor up if anybody has any questions about racing.
Two or three questions. Eric, this hand was...
Jeff, I have that was an amazing, fascinating, detailed talk. Thank you so much.
Yeah.
Quick question. So I'm just trying to understand what you do in a general sense. What I mean is, you do all the data analysis, which you shared with us. So let's say you find out, oh, this car is just too fast. Engine's too good, it's too aerodynamic. Then what do? You tell them you need to tune down your car in some way? And then who decides how that happens? Do they make it? Can they make it heavier? Can they decrease aerodynamics? Can they tune the engine? That's up to them? Or how does that negotiation work, and what's that process?
Okay, first of all, it used to be a negotiation. Now it's no longer. Oh, I hate these things. It used to be a negotiation. By the way, did you guys all hear the question? Yeah. Okay. So now we have a whole committee that operates internally, and we've collected more data on the front side. So we've gone to the wind tunnel. We know what the adjustments are on the wings. We know we've been to the dyno, so we know what the restrictor numbers are. We know how much power it makes at any particular RPM. We know what size tires are on the car. And when we measure performance at what we call out of the box, so it's outside of the beep, be it too short of a beep or too long of a beep, we can using what's called chassis simulation. So we've modeled each car. So we'll model every car in a chassis simulator, and we can model each engine. So we'll make a change in the sim, and it'll give us a percentage change in lap time at any given track. And then we can come to the table and tell the team, hey, your restrictor size is going up 5% or down 5%, or you're getting a narrower tire, or we're going to increase or decrease weight. When we were looking at sector analysis, like those twisty bits, if a car is like crazy fast for the twisty bits and really slow on the straights, well, what we would do is put weight on the car in the twisty bits and give them a little more horsepower so they're faster on the straights to level out the raceability.
You would want to exaggerate the differences so that the race is more interesting with,
There's a window, right? And we want everybody within the 0.75% window, but if they're 1% ahead of the field in one, then that's not really raceable. Right, so we have to keep them in the window, but we have the window for a reason. It's not a zero window; it's a pretty broad one.
And you're adjusting them per track, so that like this car, which is better on twisty bits, is better on a track with more twisty bits, right?
Yeah, absolutely. So the box, like, okay, at the end of the race, we take everybody's laps. It could be like 100 laps in the race. The top 20 laps that they do, we average that out. We express the difference as a percentage. The percentage difference is 0.75%. And the order within that 0.75% box changes all the time. If it's one car all the time on the top, then we got a problem, right? But if it's a Porsche one weekend and a Mustang another weekend, and then the Camaro another weekend and Nissan the next, then that's good competition. But the order within the box changes, but we want everybody in the box.
Let's go there to Nick.
Do you ever have a situation where you just say, okay, it's going to be all Camaros in this race, and everybody go as fast as you can?
My life would be so much easier. Yeah. I mean, do you, like us tell the teams what cars to run?
Yeah, or like if you have a Camaro, you can race in this race.
Yeah, well, that's the way it goes. Teams are free to pick any car they want, but they normally have a sponsor that maybe is a partner of BMW in the real automotive world. Like there's one of the teams is sponsored by this company that provides all the paint for BMW in Germany, right? So they only want to race BMWs because that's the product, right? So other times a team owner, like he may own a Chevy dealership and he wants to take his Chevy dealership racing, so of course they're going to race a Chevy. So sometimes we can't break those bonds. Other teams are free to choose which manufacturer they want. Ooh. You.
So you talked a little bit about marking those sectors.
Mm-hmm.
When you do that, how do you determine the sectors that are going to be marked, and how sort of is that just like a very sort of mathematically determined process, like where there's not a lot of sort of feel to it, you just sort of know where they go, or is that a thing where you're sort of iterating or adjusting the sectors of the track where you're taking these measurements?
No, actually, it's very targeted, right? So we start with CAD data from every track. Every track has a 3D model that's done, right? So we were able to very clearly identify areas of performance that we want to examine. Now we went to every track that we go to before the season, and so every year we have the same sectors there. It's important we got it right in the beginning, because the teams we share that sector data with all the teams, so we want it to be consistent. So it's targeted. We have very specific ones. We'll look at on the data analysis, on the onboard data compared to the CAD drawings, see actually when they apply the brakes and when they actually get on the gas and when they stop accelerating, when they're in danger of spinning the wheels, and we'll drop the sectors in exactly at the limit of where the performance characteristics are in danger of being skewed. Right. But in fact, at COTA, there were 2 speed traps at COTA on the straightaway. We screwed up. Right, so the first one at the end of the straightaway, and see if I can go back to it. Right, so this, I'm glad you asked that question, because we screwed this one up. This is an example of us putting something where it shouldn't have been. We thought the cars would get to brakes about here. It turns out that they got to brakes right about here. Right, and the teams came up to us after the first race we ran there, and everybody, absolutely lit me up. Oh my God, this other Porsche is so much faster than ours. It was 6 miles an hour faster in the speed trap than our Porsche, and it should be the same car. What are you not doing right? I went out there, and I don't know why they didn't go actually out there to look at it. Went out and stood out here at the fence, and I was watching the brake lights come on right before the stripe. So it was definitely our mistake. So we had to create this other speed trap here that's out of the brake zone.
Not to ask a stupid question.
Okay, there are no stupid questions. Come on.
Okay, so a lot of this talk and a lot of the material is about sort of optimizing every car going the exact same speed and everyone having the exact same chance to win. So if they all have the same speed, they all operate the same way, if everyone's trying their best, at what point is victory then just chance? Or, I guess I'm asking what skill is involved if it's not in the craftsmanship of the car.
Because racing's more than driving, right? So we can put the tools in the driver's hands that everybody's going to have a shot. But the guys on the pit box and the guys that are changing the tires, the guys that fuel the car, the crew chief that decides when all that happens, that's what's going to win races, right? Who worked hard in practice and figured out how to not wear the tires down as much as the other car, so they can make adjustments to the cars that may give them an advantage over a long run, that may sacrifice ultimate lap time. So this is the craftsmanship of racing. So we want to, in an ideal world, all cars being equal, we want to have everybody to have a shot. But the good teams are always going to be the good teams. And this is why race results didn't show up in our performance analysis. It's not about how they finished, it's about the data that they produced.
Could you give an example of when the driver or the team has kind of deviated from the path that you thought they had set out for them? So like when driver error or when excellent performance kind of surprised you or changed that around?
Oh, yeah, that's a great one. The Camaros this year, in a couple of clips, they did really well. They won the championship, but most times in the data, they were pretty well off. That was a team that they just executed. So they were on average, let's say, instead of the 0 car and the average numbers, average lap times, we call the 0 car the top average car. They were on average 0.5, 0.6% off the fastest car on track, but that was just the execution. It was shocking to us that they could continue to win over and over and over with a car that was clearly 0.5% off the winning pace, off the fastest pace.
Yeah, are you guys running the instruments that monitor
Oh, yeah.
Okay, so what is the incentive that the racer has to fudge the power of the car?
Oh, see, because this is relatively new. Right. Oh, actually, here you go.
If the instruments are monitoring the car every single race, then what incentive does the racer have to fudge the power of the car to the organization?
So the one manufacturer on the dyno sheet that I showed you where they had fudged the number, they didn't expect us to take the motor to the dyno. Right? So what they did, well, actually, if you don't mind, I'll give a quick cheating story, little war story for everybody. So that particular team and manufacturer, the performance of the car was extraordinarily strong, and this was before we had some of the procedures in place. Now, like before a car goes on track, now we go to the dyno with it because of these guys. And so we started with one performance balance. It was an 80 millimeter restrictor, and then eventually, the smaller the restrictor number, the less air gets into the engine. All right, so we started with this one number, and then the car was really fast. We pulled it down a little bit more, and because it's a reputable manufacturer, we thought, hey, let's reach out to them. Let's get some power numbers and see if we can set some expectations and changes in performance as we change the restrictor size. We trusted somebody. Well, they sent us some info. You know, we as we went through the season, the car was we'd adjust it and it wouldn't really get any slower. Well, we get to one race and they qualified first and second. After for those that don't know, after qualifying the race, we impound certain cars. So we take them in to our tent and we can take them apart. We can pull the pistons out of them, or have the teams pull the pistons out if we want to. So we took the restrictor out and measured it, and one of them had a big restrictor in that was way bigger than they were allowed, and one of them had the right size in it. And when I overlaid the data, it didn't matter. They were both. I mean, they were within a mile an hour, and they were supposed to be 20 horsepower different. So how in the world does that happen? So after that race, we took those motors to the dyno, and we found out what they had done was severely understated the impact, or the power and the impact of what the restrictors actually did. So they were able to run these engine calibrations. So they were able to run software that turned the power down, right? So every time we went smaller on the restrictor, they could just dial more power in with software. No, actually, okay, small story about that. I used to work in with a company that specialized in VW stuff, and spent a lot of time there. And we always called that tuning protection, because we sold aftermarket engine tunes. So if you we could plug in with a laptop and make your car go faster. And we had found these maps in the ECU that we could play with and make more power, but on the dyno it would work fine. But once we drove on the road for like 5 minutes, it would all go away, and we were back to stock. What we didn't realize at the time, 6-7 years ago, was that we were modifying the emissions sheet calibrations and not the ones that were driven. Now we had it right there. We had no idea what we're looking at, but that's what we did.
That's all we've got time for, unfortunately. So thank you all.